This is lecture 37, and today we'll be covering the concept of capacity. It's one of those fascinating topics from information theory, but actually is used quite extensively in wireless channels, and how do we optimize and get the maximum out of a wireless channel. The goal would be to not only understand capacity, but also to understand what are some of the challenges and how do we overcome that in the context of a wireless channel. So first, let me quickly summarize one of the concepts that we have talked about, the last concept in diversity. The key takeaway from the discussion on diversity is that we could think of the benefit of diversity in terms of two components. One is in terms of an array gain, the other one in terms of a diversity gain. The instantaneous SNR gamma k can be written as mod zk whole squared. That's the amplitude square of the channel gain, times Es by N naught, what nominal SNR multiplied by mod Zk squared. We find that gamma MRC, which is the optimal diversity combining, gives us the sum of the instantaneous SNRs, k equal to 1 through m gamma k. Notice that this is the instantaneous SNR, because if I take average SNR, I will get m times gamma. So this can be written as Es by N naught, the average SNR in the absence of fading, summation k equal to 1 through m mod Zk squared. Again, these are all just results from diversity combining. And the important result, expected value of gamma MRC. This we write as m times gamma times summation k equal to 1 through m mod Zk squared divided by m. Okay, and of course, this is important form that we get, which says that I get a component which is array gain, and then the other one is the diversity gain. That's an instantaneous benefit. Array gain is an average benefit. So this is the diversity gain. Okay, so here is the way that we have visualized it. So if I look at two-branch diversity, then the graph without diversity is the green line. If I have only the array gain, which is a 3 dB advantage, that will be a parallel shift of the BR graph, but then the MRC actually changes the slope as well, and therefore we get the additional benefit which we attribute to diversity gain. Okay. So total diversity benefit is array gain plus diversity gain. Again, keep that picture in mind. So for the special case of m equal to 2, the benefit due to gamma MRC would be 2 times gamma times mod Z1 squared plus mod Z2 squared divided by 2. So this would be the SNR that we would get, so for gamma MRC. Okay. Now if you go back and look at our Alamuti scheme, the Alamuti scheme was a scheme where we had 2 transmit antennas and 1 receive antenna. NT cross NR is 2 cross 1, as opposed to the MRC scheme. This would be the MRC scheme, which would be 1 transmit, 2 receive, 2 received signals. So this was the scenario that we looked at, and we showed that the SNR for an Alamuti scheme, the SNR for the Alamuti scheme, instantaneous SNR, comes out to be gamma times mod Z1 squared plus mod Z2 squared divided by 2. Notice that 2 gamma is missing, that 2 is there missing in the array gain. So that is why we said that the Alamuti scheme, which is in general, so we could write it here as Alamuti scheme, it does not have array gain, but it has the diversity gain. This is mod Z1 squared plus mod Z2 squared is the array gain. Z2 squared, okay, as opposed to the received diversity schemes like MRC, which give you both diversity gain and the array gain. Okay. And maybe there is a simple way of visualization which I thought might be helpful for us to look at. Let me just add a new page and okay. So this is the traditional received diversity scheme. Received diversity scheme, let's assume we are doing maximal ratio combining. Okay. So we have 2x Rx signals. There are two antennas, so there are 2x Rx signals. They have been combined in a co-phased manner. So therefore, when it comes to computing the signal power, I get a 4x times Rx signal power. Is that correct? I have co-phased the two signals, so effectively I have got twice the signal level, and when I take the signal power. Okay. How many noise terms? I have 2x noise terms, noise power. So the net benefit is 2x, 4x in the signal component, 2x in the noise component. So therefore, this is a case where I get array gain and diversity gain. Diversity gain. Okay, so both are present. Now, on the other hand, if I had a transmit diversity scheme such as Alamuti, okay, how many? What is the total received power that I have? 1, because I have got a 1 over root 2, which is a scale factor. When I look at it in terms of power, it's half on each antenna. So I get 1x times the Rx power. And of course, since there's only one antenna, there is only 1x noise source. So noise power, so the ratio is no array gain because it's 1x in the signal power, 1x in the noise power. So therefore, I do not have array gain. No, but diversity gain, yes, because I have actually combined mod Z1 squared plus mod Z2 squared. So again, this is just repeating what we have said just now, but again to visualize saying, okay, where is the benefit coming from? So in other words, the advantage of the two antennas, is that I am actually intercepting twice the amount of received signal power. Whereas if I have only one antenna, then I get the power benefit of one antenna. So that is another way of visualizing it. But again, I would like you to be very comfortable saying, when do you get a diversity gain, when do you get array gain, and which contributes to what, and how do we exploit that in the system. Okay, another element that we had introduced in the last class was the notion of feedback of information about the channel, feedback to the transmitter. So here is TDD systems are very straightforward because of the channel reciprocity. We assume that when the receiver transmits, when the mobile transmits to the base station figures out what the channel is. But FDD systems are a little bit more involved. FDD systems, the downlink happens on frequency F1, uplink happens on frequency F2. So transmitter is base station, sends some information through a channel to the receiver. Now the channel is the behavior of the channel at frequency F1. So this channel state information corresponds to F1, frequency F1. So the channel response is estimated at the receiver. It is F1, channel response corresponding to F1. But this information has to be fed back to the transmitter. So that any communication between the mobile and the base station is happening on F2. It may be sending other information, but it is also sending the channel state information for the downlink. So yes, the channel state information pertains to F1, but it is going to the base station on a different frequency. It happens to be F2. So CSIT basically means that whatever has been the channel response that has been measured by the mobile is been fed back to the transmitter, and therefore both transmitter and receiver have got knowledge of the channel. Okay, TDD systems are straightforward, both uplink and downlink are on the same frequency. The reason for reviewing this is to ask you the following question. Alamuti scheme, does that require CSIT? Did it use information at any point? If you go back and look at I don't have the slide from Alamuti scheme. Notice that all it was doing was it was doing a time reversal and a conjugation of the symbols being transmitted. It did not require you to feed back Z1 and Z2. So maybe a good point to note down is Alamuti scheme does not require CSIT. Alamuti scheme does not require CSIT. In fact, it is so general that it works for any modulation, it works under all channel conditions. You don't need to worry about it. The only assumption that it is making is that it is flat fading, because it assumes that there's only one channel coefficient between the transmitter and receiver. So it does not require CSIT. Okay, that's one point. The other point is that it works, the Alamuti scheme, it works for any modulation scheme. For any modulation, we did not make any assumptions about the modulation scheme. It works for any modulation method. It can be QAM, it can be PSK, and it works under all channel conditions. Works for all channel conditions. All channel conditions. The only assumption being it's flat fading. Channel conditions. Let me just put it within bracket that we have assumed that it is a flat fading channel. Okay, so if you have a flat fading channel, then what you get is based on the transmission scheme that we have developed, you get a channel matrix which happens to have the orthogonal property which they then can exploit to detect the signal. Did it require CSIR? Does the channel scheme requires CSIR? Yes, it has to estimate the channel. Only then it can do the conjugation and multiply it by the appropriate thing, so by the appropriate channel coefficient to get. So yes, it does require CSIR. It's a coherent scheme in that sense. So, but it does not require information at the transmitter. Okay, the last part that we had discussed in the previous lecture was our understanding of channel capacity. Again, we just referred to the basic discussions on concepts of capacity that you would have studied in digital communications, which is linked to the concepts of entropy and mutual information between transmitter and receiver. And based on this assumption, without any constraint on the delay or the complexity of the encoder decoder, the channel capacity, according to Shannon, is given by bandwidth times logarithm base 2 1 plus SNR. So again, this is a very useful form. If you take C by B, which is a normalized capacity, then the units are bits per second per hertz. Otherwise, it would be in bits per second. Gamma is in SNR, a dimensionless quantity. Okay. So based on this, we had a couple of examples. Maybe just let me just mention that the first example that we looked at, example 1, there were two cases at a distance of 100 meters. We found, or we computed the SNR to be 15.23 dB, and given that the bandwidth was 30 kilohertz, we found that the capacity C1 came out to be 153 kbps. Okay, 30 kilohertz. It says according to Shannon's capacity, you can actually pump 153 kilobits per second through that, but at a distance of 100 meters. For the same channel model, the model itself is not that important. The important one is the concept that we are taking away from there. The SNR came out to be minus 14.77 dB, and the capacity drastically dropped to 1.42 kbps. Okay, again, the numbers are easy to plug in and substitute, but the most important thing is the observation that SNR plays a very, very important role in the capacity of the channel. Okay. Now, this is a case where the SNR changed because of what? Path loss, because you moved away. But it could very well have changed because of fading. So now once you have understood this, Now we then move the context saying, don't worry about path loss. It's not path loss anymore. It's going to be in the context of fading. And what is going to happen? The fading environment, at least in the case of path loss, I know it's going to go, I know I can predict, but this is path loss. Path loss. So the capacity at this point is very different from the capacity at this point because the path loss has changed. But in the context of fading, I have a capacity that is fluctuating. Okay, it is fluctuating. So at each point, based on the SNR, then I get a certain capacity. So it is no longer a fixed quantity. It is something that is constantly changing. It's like the SNR in a fading channel. So that is where we are going to really engage with the concept of capacity. So what we can summarize from this example is if the SNR goes down, then in this particular case it went because of capacity, the capacity goes down. Okay. Now SNR can go down for one, it can be because of path loss, as in this particular example, or it could be due to fading. It really does not matter what is the cause of it. It's going to eventually affect my capacity. Okay. So with that broad framework in mind, I would like for us to look at one more example. Again, the purpose of this example will become clearer as we look at it and spend more time with it. Okay. So here is the example 2. The bandwidth is 30 kilohertz like the previous example. And we're going to look at 3 different SNRs. You may wonder, why that we already saw 2 SNRs. What difference is going to make for 3? But the important thing is how we're going to interpret these results. So if this is a channel where the SNR without fading, that means in the absence of fading, is a high SNR system, 25.2 dB. Now this on the linear scale corresponds to 333.3, and we will calculate. Now the instantaneous SNR with fading, so we can call this as gamma. This will be equal to alpha squared gamma. That's the instantaneous SNR. Okay. So this is an example where there are 3 SNRs possible. Alpha 1 equal to 0.05, alpha 2 is equal to 0.5, and alpha 3 is equal to 1.0. So it's either at the nominal SNR or worse than SNR. Again, it's a constructed example. It's more for illustrative purposes. Now, what's going to be very important is the next column. The probability of alpha 1 is 0.1, probability of alpha 2 is 0.5, probability of alpha 3 is 0.4. These are the 4 possibilities. Okay. Now, just quickly compute the capacities for each of these. This corresponds to 0.833, and this corresponds to a channel capacity of 26.2 kilobits per second, okay, because of the low SNR. This corresponds to 83.3. This corresponds, and the capacity for this is 191.9 kbps, and the alpha equal to 1. Of course, we have already computed 333.3. This is the SNR column. This corresponds to a capacity of 251.6 kbps. Okay, so the problems before us is the following. I have 3 states if you want to consider. It's not good state, bad state, there's some intermediate state as well. The capacities are 26 kilobits per second, 192 kilobits per second, and approximately 252 kilobits per second. Now the key concept is how do we even deal with or come up with something which has a reasonable representation of the capacity of the system. So this is where we go back and say that this column, this capacity column, can actually be written as a capacity as a function of gamma, which it is, function of the instantaneous gamma. Now gamma has got a probability distribution, f gamma of gamma. Okay. So we can actually come up with a probabilistic capacity for this channel based on the channel states, which is called as ergodic capacity. Ergodic capacity. It is a capacity, it is a number that reflects what is the behavior of the channel. So the ergodic capacity is defined as over all possible SNRs, the capacity at that particular SNR, the probability of that SNR integrated over the range. So basically what we are saying is if a particular SNR is very highly probable, then the ergodic capacity is going to be very close to that number because that SNR is very likely. If a probability is very less, then that's not going to be as dominant a factor. So this is for a continuous distribution of SNRs, but here this is an example where we have a discrete number, so therefore I would like to calculate the ergodic capacity. So the ergodic capacity for this channel will be 0.1 times C1 plus 0.5 times C2, this is ergodic capacity, plus 0.4 times C3. Again, it's a simple calculation that you can compute and verify, and this comes out to be 199.2 kilobits per second, 199.2 kbps. Okay. Now the reason this the bad channel did not dominate or did not cause a significant degradation was because the probability is less. It's only 10% of the time, so it did actually pull down the overall capacity, but the better channels sort of tended to dominate, and therefore we got a good number. Now it's very interesting for us to do a very similar calculation. Now the question that we are going to ask is, what is the average SNR? What is the average SNR of this particular channel? So basically gamma will be 0.1 times gamma 1 plus 0.5 times gamma 2 plus 0.4 times gamma 3. Right? That's the average SNR in this particular in this channel. So if you were to look at this, this comes out to be 175.08. Very interesting question. What would have been the capacity for this particular average SNR, C subscript gamma? So this will be equal to B times logarithm base 2 of 1 plus gamma. And so what is the question that we are asking? We are saying that we are doing two types of calculation. One is I have a channel that is varying. I have 3 different SNRs. What I have done is computed the capacity for each of those SNRs and then done an average of it based on the probability. Okay? One is an averaging of the capacity. The other one is an averaging of the SNR and then computing the capacity. So this latter case, which is in green, is like an AWGN channel which has got average SNR equal to gamma. Okay, so this is what would be the equation or the capacity equation for an AWGN channel with this gamma. So this is like an AWGN channel. There's only one channel number, one capacity number channel with SNR equal to gamma. Okay, and it's very interesting for us to compute that. This comes out to be 223.8 kbps. The observation. An AWGN channel, we know that in the context of fading, even if it has same average SNR, AWGN channel is much better for us to deal with because the fading actually degrades the performance. It seems to be doing something very similar for capacity as well, because the capacity of a similar channel if you just take it on the base of SNR, is giving you much higher capacity in the context of an AWGN channel as opposed to the ergodic capacity. Okay, so the question that we would, or the other way that we would make this statement would be as follows. At least in this particular example, what we have found is that the expected value of the capacity is B logarithm base 2 1 plus gamma. Okay, that's ergodic capacity. So this is ergodic capacity. It turned out that the ergodic capacity in this particular example is less than B times logarithm base 2 of 1 plus expected value of gamma, and this is nothing but gamma. Okay. One case it was 199 kilobits per second, other one was 223 kilobits per second. Now, is this always true, and if so, what are the implications? Lot of very interesting questions that arise from our discussion, but it's very important that we sort of get a feel for what is the concepts that we are dealing with. So here is a summary statement. We know that fading compared to AWGN in terms of SNR, we have done fair amount of that. We looked at the bit error rate. Now, just like fading affected the bit error rate, it seems to be affecting capacity as well, and the capacity impact also is along the similar lines as the impact that it had on BER. That fading is actually makes the performance much worse than the corresponding AWGN average AWGN channel. Okay, so again, how do we develop this? How do we build it up into a concept that we can work with? This is the crux of today's lecture. Okay, so we now move into another important concept, again, which you would have seen in information theory, but I would like for us to look at it again in the context of what we are studying. So this is a concept known as Jensen's inequality. Jensen's inequality will actually give us a definitive answer to the previous question that we said. Is it always true that ergodic capacity is worse than the capacity of an AWGN channel with the same average SNR? So Jensen's inequality will give that. Okay, but before that, let's first build up our intuition. Logarithm function. If I were to plot the following logarithm function, x logarithm base 2 of 1 plus x, okay, you will get a graph that looks like this. Basically, so you can just do a sketch and you will find. Okay, if you and the following result is true. So supposing you consider 2 points. So basically, x is greater than 0. Basically, it's the positive real axis. Because we are looking at it can do greater than or equal to 0, positive real axis, and if you look at 2 points x comma y, without loss of generality we assume y is greater than x, we can make the following statement about the logarithm function. Logarithm of x plus y divided by 2 is greater than or equal to log x plus log y divided by 2. Okay? Just to be sure that you are comfortable with the result, take x equal to 100, y equal to 1000, x plus y by 2, logarithm base 2 will be x plus y by 2 is log base 2 of 500. You can verify that this is greater than log base 2 of 100 plus log base 2 of 1000 divided by 2. Okay. Basically, log base 2 is really not immaterial. You can look at it, and any base logarithm has this property. Okay. Now, this property is called concavity property. Basically, logarithm is a concave function. logarithm is a concave function, and this property that what we have written down is the general property of concave functions. Okay. Here is the Jensen inequality. So it's always good for us to have the context in which we are result is being stated. Jensen's inequality states that for a concave function, and for us we are very specifically interested only in the logarithm because we are looking at capacity. So for any concave function psi of a random variable x, the expected value of psi of x is less than or equal to the function of the expected value of the random variable. Okay, this is Jensen's inequality. Concave function, expected value of the function is less than the function evaluated at expected value of the argument. Okay, expected value of x, and this is the now the key thing is what is it that we are trying to study or equate. I want to know what is the ergodic capacity. Ergodic capacity is expected value of logarithm base 2 of 1 plus gamma. Logarithm is a concave function, so therefore it satisfies the Jensen's inequality. This is less than or equal to logarithm base 2 expected value of 1 plus gamma, which will be the same as expected value, or this will be the same as 1 plus gamma, which is the capacity of a AWGN channel with the same average SNR. So Jensen's inequality more or less confirms that ergodic capacity will always be less than the corresponding AWGN channel with the same average SNR. So we can write down that statement. So ergodic capacity is less than or equal to the capacity of AWGN channel with the same average SNR. Same average SNR. Okay. Now, why is that very important for us? The capacity of a AWGN channel, very easy to compute. You just calculate average SNR and you can compute. That's an upper bound. So what you try to do is whatever system you design, you want to see how close you can get to AWGN. Remember, it's just like BER graphs. You want to know how close you can get to BER graph because that's sort of the performance bound, if you will, that we have. But at the end of the day, what is it that we can optimize? We can only optimize ergodic capacity. So that is where the challenge will lie. That's where the interesting concepts are going to lie. So here are the three cases that we will, three possibilities that we have for studying ergodic capacity. Three cases. And very specifically, we'll be focusing on one of them. But let's write down all the three cases. Case one. The PDF of gamma, the PDF of the instantaneous SNR. For example, if it's a Rayleigh distributed Rayleigh channel, then the SNR would be the chi-square distribution. So the PDF of gamma is known to the transmitter and receiver, known to Tx and Rx. Okay, this is a case where the instantaneous channel state information, that is gamma information, this is gamma, is not known at Tx or Rx. Now, if you don't know the SNR, what would you do in a practical scenario? You'll measure it. Okay, but in information theory, it's perfectly fine to assume that you don't know the SNR, you don't want to measure it. You just say, okay, if I have only PDF, what do I do? How do I achieve capacity? And it turns out that according to the information theory experts, this is a very, very difficult problem because you don't know what the instantaneous SNR is. So therefore, it is one of those situations where you have to design such a complex system that it will survive even in all kinds of SNR conditions. So number one is really not of much use to us. Maybe we just make the statement that it is a very difficult problem. In fact, for most of the channels that we encounter, it is still an open problem, okay? Very difficult problem. So maybe it's the question is, why do we assume? You can always measure. So the second option that we have is that I can measure the SNR at the receiver. So which means that this is CSIR situation. So both Rx and Tx know the PDF, like before, they know that it is Rayleigh statistics or Riccian, whatever it is. Both Rx and Tx know the PDF of gamma, and Rx knows the instantaneous value. Rx knows the instantaneous value of the channel conditions or the gamma. Instantaneous channel condition. Okay, so it knows the PDF, it also knows the condition for gamma. Okay, now this turns out to be a very, very interesting situation, because under these assumptions you can ask the following to be computed. One is ergodic capacity. Okay, you know the SNR, you know what is the distribution of the SNR, so therefore you know what the ergodic capacity is, and therefore you should be able to try to design systems that will try to achieve. So ergodic capacity becomes a interesting problem once you have a measurement of the instantaneous SNR. The second, probably the more practical example or the result comes from what is called capacity with outage. Capacity with outage, and it's a very, very interesting concept. This is something that is at the heart of trying to design practical systems and trying to get the best out of the wireless channel. Let's just finish the discussion. The third case is probably the most interesting case, where you have measured it at the receiver and you have fed the information back to the transmitter. So the transmitter knows the instantaneous value. So Rx and Tx, they know the PDF, they also know the instantaneous gamma, instantaneous channel state information gamma. Both of this information is known to the transmitter and receiver, and under these conditions, what is the best that we can do? Okay. So again, is the problem statement clear? I have transmitter, I have receiver, I want to maximize the notion of capacity. Now in the absence of knowledge of instantaneous SNR, it's a very difficult problem, not going to spend too much time on that, but CSIR is a very important case where we can compute ergodic capacity, we can compute capacity with outage, and of course the best system is when you have knowledge at the transmitter and receiver. Okay, so now I would like for us to look at a particular example. Again, a simple example but very illustrative in terms of the concepts that it communicates for us. There are two channels with bandwidth B, bandwidth equal to B. Both channels are the same. The average SNR is the same for both, for Tx power P. So that means if I transmit with power P on both of the channels, the average SNR is going to be the same. So basically both are experiencing the same fading, the statistics are the same. Okay. So, but here is the system. Gamma 1 for SNR is 20 dB, the average SNR, and gamma 2 is 5 dB, the average SNR. Okay. So the capacity for this particular channel, capacity will be in terms of B times logarithm base 2 1 plus 100 this comes out to be 6.66B. Capacity, and this is going to be logarithm base 2, 1 plus 10 raised to the power of 0.5, which is 2.06B. Okay. So now if I were to feed P and P to both of these wait. I'm sorry. The average SNR for Tx power P is given by this. Okay. It's not both have same average SNR. So if I feed equal power P to both the channels, channel 1 gives me 20 dB SNR, channel 2 gives me 5 dB SNR, and the corresponding. So I have I can give P to each. So then the capacity that I will achieve as a combination of these two channels comes out to be the sum of these two capacities, which is 8.72B. 8.72B. Okay. So here is the interesting calculation. Instead of feeding P, let us assume that I will feed P1 to channel 1, P2 to channel 2, with the assumption that P1 plus P2 must be equal to 2P. I can distribute the power, I can vary that. Based on that, I will get C1 and C2, C1 plus C2. Okay. So that's the assumption that we are making. Let us see how this plays out in our calculations. So the first line is if I give P and P, channel 1 gives me 6.66B, 2.06B, 8.72B is the capacity. That's the previous one. Now first off, I'm going to try an experiment. I'm going to double the power in 1, which means this is going to go to 0. So what will happen to the SNR on channel 1? It will increase by a factor of 2, because I have increased the power by a factor of 2. And I now want to see what's the impact and calculate or capacity. It comes out to be 7.65B, and for C2, 0, right? Because you took away all the power. You didn't give any power to this one. So what is the net capacity that you achieved? C1 plus C2, 7.65B. Okay. What is the logic here? I have a good channel. Let me give all the power to the good channel, and therefore, hopefully I will get a better capacity. Well, it turned out now that's not the case. Giving equal power to both of them actually does much better. Okay. Now, of course, you may want to say that, well, you know what, take away power from the good channel, give it to the bad channel. You may want to do a little bit of that. Let's see if that is going to help. Say, okay, instead of, I'm going to give 1.5P and 0.5P. So basically, we say the good channel, give it a little more power, but don't take away all the power from the bad channel, give it some of it. And it turns out that this comes out to be 7.24B, 1.37B. Again, you'll have to basically you're plugging in different scale factors into the SNR, and this comes out to be very close to optimal, 8.61B. Never not optimal, very close to the case of equal distribution of power. Okay. Now let's reverse the logic, saying, well, who needs more power? The channel which is bad condition. So why not take little bit of power from here and give it to this one? So 0.5P and 1.5P. Basically, you are trying to equalize the powers. Is that the right strategy for us to do? So this comes out to be 5.67B. This one improves a little bit, 2.52B. The net benefit or the net capacity is 8.19B. Okay. So, well, clearly taking power away from the good channel and giving it to the bad channel is not a strategy that you want to follow. So what have we learned so far? You must use both the channels. Worst case, you give equal power to both of them. Maybe if you play around with the power levels, you may see some benefit. And of course, if you try hard enough, you will come to this particular case, 1.2P 0.8p, this comes out to be 6.92b, 1.82b, and this comes out to be 8.74b. Okay, actually it turns out it beats the equal power allocation. So maybe here is the points that we want to take away from this discussion. Why didn't this case work? I gave 2p to the good channel, right? Why didn't it work? Why didn't the capacity, I'm surprised by that result, am I not? Because I've given all the power to the good channel. Capacity is logarithm, it's log of the power, right? So, the bandwidth term is sitting outside. So, if you have 2 times bandwidth, that's going to play a bigger role because the power is embedded inside a logarithmic function. So, here you can maybe say C is linear in B, it is logarithmic in SNR, and therefore, it's not a good idea to take away a channel completely. Okay. Now, obviously, this one says that if you don't want to take it away from, use both channels. Use both channels. That's going to be the strategy. But do not try to equalize the power, because that's again giving more power to the bad channel is not going to help us. The right strategy seems to be give more power to the good channel, but also use the bad channel so that you get the benefit of the linear term in bandwidth. Okay. So, observations, use both channels. Use both channels. Second, give more power to the good channel. Maybe that's a little counterintuitive, but that's a very important result that emerges from there. Now, is this true in general? It turns out that yes, this is actually the insight that we need to work with the wireless channels. More power to channels with higher SNR, with high SNR. Okay, that's a very, very powerful result. The other one also is a important result that we want to work with. Okay. Now, let me just leave you with once you have this framework, I want to leave you with the following summary. So, the case of CSIR, how can we summarize the CSIR? CSIR says that ergodic capacity is what we are trying to achieve. Ergodic capacity is given by integral 0 to infinity b times logarithm base 2 1 plus gamma f gamma of gamma d gamma. That's our basic equation. F gamma of gamma is known to the transmitter and receiver. The instantaneous value of gamma is known at the receiver, but not at transmitter, because you did not feed back this information, but not at the transmitter. So, given this situation, what can the transmitter do? Transmitter says, I don't know what the channel is. So, what will it do? It says that, sometimes it's good SNR, sometimes bad SNR, but I must transmit error free, right? I must get the information across to the other side. So, what the transmitter has to do has to go for worst case design. Whatever is the worst possible SNR, I have to transmit at that rate, because I don't know if it is better or worse than that. So, the system has to, because I don't know it so the system has to operate at a fixed rate, has to operate at a fixed rate. Okay. So, if that is the case, let me go back to the example that we calculated. CSIR, what rate will you achieve in this channel? 26 kilobits per second. So, that's the worst case SNR, right? You don't know whether the SNR is alpha 1, alpha 2 or alpha 3, the channel condition, and you have to transmit reliably under all the channel conditions, otherwise you will go into outage. You don't want outage. So, now comes the important concept. If you want ergodic capacity, it will be based on worst case SNR, because the transmitter does not know which is what the instantaneous SNR is. However, if you now tell the transmitter, oh, by the way, some outage is okay, you transmit under what you think is a good scenario, and if occasionally the data gets lost, it's okay. What capacity can you achieve? Same example, what's the capacity that I can achieve? I can do 191.9, and what will be the outage probability? 0.1. 90% of the time the data will go through and it will go at 192 kilobits per second. So you can see how if I allow a little bit of outage, the channel is going to perform much better. Okay? What's the intuition? Don't try to communicate under all channel conditions, particularly in the presence of fading. There may be some conditions under which the transmitter does not know it's such bad situation, but it's okay, outage is fine. What will you do if outage happens? What will you do? Data is lost. What happens if you do data is lost? Retransmission, no problem, we have a solution for that. So you take outage, but take it so that you get better capacity. Okay? So that is the CSIR concept of thinking, saying that okay, design for worst case. The design has to be actually quite challenging, because if you have a bad SNR like 0.833, that's less than 0 dB. Okay, so if you have such a poor SNR, then you have to have a lot of coding, and basically your code words must be very carefully designed. There will be very long code words. The decoding is going to be very complex. So therefore, this is a scenario where the design is going to be difficult, and at the end of the day you are going to get poor capacity. So a good engineering approximation says, forget doing ergodic capacity, but let's do capacity with outage, and therefore come up with some very practical examples. Okay? Now on the other hand, if the transmitter knew that the channel condition was bad, would you still have outage? Would you still have outage? No. What will the transmitter do? It will not transmit. It will not transmit. So that is the benefit of CSIT. So basically whatever you can achieve with outage, you can do better than that when you go into CSIT, because the transmitter can just say, oh, this is really bad condition, I am not going to transmit, I am not going to waste my power. And the power that you saved, who will you give it to? You will give it to the good channel condition, so you actually will get more capacity through, more data through into the system. Okay? So that's the dimensions that we are going to study, and at the end of the day, where did all of this come from? Let me just end with a little bit of history so that you can then think about it, and you'll really appreciate this is okay. The most important system or thing that we worked with in communications are the telephone lines. Right? That's where most of the inventions, telephone line, analog telephone lines. Okay? Analog signal bandwidth, voice, 4 kilohertz. Okay, 4 kilohertz. That's why we do 8 kilohertz sampling, and the total bandwidth that you are using is 4 kilohertz. Okay. Now this is going to be transmitted over a copper wire. That's initially analog channel. The frequency response of an analog of a telephone line, copper line, is this axis is greater than 5 megahertz. Okay, it's got huge bandwidth. But the problem with this is this bandwidth has a response which is very bad. Okay, the gain is very poor at high frequencies. So what do? We use only the useful portion, and all of this is waste. On a copper line, we transmit only 4 kilohertz when it has got so many megahertz of bandwidth. Okay? So the question that always was at the back of people's minds is, what is the capacity of this telephone line? What is the capacity of this telephone line, and how can we achieve, or how can you improve? Right now you are using it for 64 kilobits per second. What is the capacity of this one? It turns out that the capacity of a telephone line is in the tens of megabits per second, but what you are doing is transmitting it at a very low part of it. So the the question became, how do we achieve capacity for such a system? And that is how, once you understand that there is a really a problem, that a real life problem that needed to be solved, then we now go back to next class. When we come back, we will talk about CSIT and all of that. So at the back of your mind, you keep asking the question, how do we achieve capacity of a telephone line channel? And the answer to this came from Shannon, which says the way to do this is through his way of, first of all, computing capacity, and then secondly, achieving the capacity for such a system. So again, it's a beautiful concept which I hope you will appreciate as we build upon it. So the answer to this question comes in tomorrow's lecture. We'll see you. Thank you.